Hi there. So in this section, I wanted to provide you with a preview of the transformation section that we'll be looking at in your class. Transformations build from what are referred to as parent functions, and in your 171 class you should have a handout for this section in regards to what the parent functions are. Here are a list of a few of those parent functions. I think I didn't miss any, but anyway, these are your parent functions up here at the top, like y equals x squared, y equals x cubed, square root of x, 1 over x, absolute value of x. These should be functions that you, whenever I say y equals x squared, you should immediately know, okay, I'm talking about a parabola and it's facing upward. Whenever I talk about the line y equals x, that should be a straight diagonal line, oops, like so, going through, and so on for the others. I've got an entire handout for you in your 171 class that talks about these parent functions and what they look like. In other words, just want to make sure that you have under your belt what these, you should have in your toolbox what these look like, okay? So where we're going to start here in example 1 is I'm going to start you actually with a parent function, and we're going to graph that parent function, and then we're going to explore what happens to our function when we take it and add 2 out to the outside of the function, when we subtract 2 to the outside. I'm going to flip it over. If we, on the next page, put in parentheses x minus 2, in parentheses x plus 2, what does the plus 2 and minus 2 do to that original parent function? Likewise, what does a negative, in example 6 down here, what does the negative on the outside of your x squared do to the parent function? I'll flip it over. Yes, there we go. In example 7 and 8, you'll notice that we put coefficients in front of our x squareds. I want to explore here, what do those coefficients in front of your x squareds do to the original graph of the parent function, y equals x squared, okay? So that's what we're going to be exploring here in this set of notes. All right, so let's go back to our first page and let's look at our parent function here, y equals x squared, and I've just set up tables here so that we could just easily generate the graph. So if we put negative, so remember this f of x equals x squared, remember that just means y equals x squared. So it just says everywhere you see an x, plug in -1, so this one would be -1 squared, 0 squared, +1 squared. So take your -1 and you square it, that gives you +1, 0 squared, 1 squared. Now let's come over here to the right and let's plot this. So I have -1, +1, 0, 0, and 1, 1. Okay. Now this is not going to be a V-shaped curve. Okay. If we wanted to add if we wanted to add another point, if I took -2 and squared it, -2 squared would give me a +4. If I took +2 and squared it, that would also give me a +4. Just so that you can see that this is a little bit more of a curved graph. And you could also put this in your calculator, y equals x squared, and generate this parabola for yourself, okay? And like I said, now what we're going to do is, as we move through this set of notes, look to see what happens when we add, subtract in various places in relationship to the original function. How does that affect the graph, okay? The 3 points on this graph that we were interested in are the 3 points here from our table. So we had -1, 1, 0, 0, and 1, 1. All right, so now let's scoot on down here to example 2 and notice that the only difference between this function and the previous one is that we have this +2 at the very end. So we're kind of curious then, what does this +2 do? I chose the same values over here for x, so I'm going to plug these values in. So I have -1 squared plus 2, 0 squared plus 2, +1 squared plus 2. So we know -1 squared is just 1, 1 plus 2. 0 squared is 0, so 0 plus 2. 1 squared is 1, 1 plus 2. All right, so now let's plot these points. Give me just a second. Let's plot these points. -1, +3, 0, 2, 1, 3. So remember, it's still our parabola, but now if we compare that, if I can get it on the same screen here, good. Now I can compare this. Notice how here was my first graph, here's the second graph. The only difference was that I put this +2 at the end, so we can surmise then, what does that +2 at the end do? it takes our graph, notice where your original vertex was at 0, 0. Now my new vertex is at 0, 2. So it shifted me up 2 units. So this plus 2 here shifted your parent function, y equals x squared, up 2 units. That's what this plus 2 out here did to us, okay? And then I have a spot down here to get these 3 points, to sort of summarize it here. This is negative 1, 3, 0, 2, 1, 3. But anytime you have a parent function and you add a number out there, then all that it's doing to that original parent function is shifting it up that many units. So if this had been plus 3, then I would have been shifted up 3 units. If it had been plus 5, I would have been shifted up 5 units. So in that same vein, what do you think the minus is going to do? Instead of shifting us up, it's going to shift us down, okay? So, here it's the same thing, that I'm going to take this negative 1 squared minus 2, 0 squared minus 2, positive 1 squared minus 2. So, of course, negative 1 squared is just positive 1. 1 minus 2, negative 1. 0 squared, 0. So that'll leave me with negative 2. 1 minus 2, negative 1. Now, if we plot these points, negative 1, negative 1, 0, negative 2, 1, negative 1. Those are my 3 values. Connect my dots. Again, if you compare that to the very first y equals x squared that we graphed, here was your original vertex here at 0, 0. Now that minus 2 shifted our graph down 2 units. So it shifted y equals x squared, our parent function, down 2 units. And the end goal whenever we do our transformations in Math 171 is that instead of having to graph these out each time, that we recognize, oh, this minus sign's on the outside, that plus sign's on the outside, that's a vertical shift. And vertical shifts perform the way we think they do. That if it's minus, we go down. If it's positive, we get shifted up. Sometimes this thing does not want it to do what I want it to do. And so it was positive there, so I shifted up, okay? And here we'll summarize here with our 3 points, just pulling from the table, negative 1, negative 1, 0, negative 2, and 1, negative 1. All right, let's flip it on over. Next page. Notice in example 4 and 5, I have the plus 2 and minus 2 here as well, but notice that it's not outside of the function. Now it's inside parentheses being squared. So let's look and see how that affects the original parent function. So I'm going to have here 3 minus 2 in parentheses squared, 2 minus 2, 1 minus 2, everything squared. So now we just clean this up. We know 3 minus 2 is 1, 1 squared, that's still 1. 2 minus 2, 0, so 0 squared, still 0. 1 minus 2 will give you negative 1, negative 1 squared, positive 1. Anytime you take a negative and you square it, it comes out positive. Let's plot these points. You notice I did choose some different values here. You'll see why in just a second. So if I plot 3, 1, 3, 1, 2, 0, and then 1, 1. Here's my parabola. I mean, I need to be going through this point over here. Sometimes, it can be a little difficult when you're just kind of doing it by freehand there. So it should look like that. So remember, your original graph was y equals x squared, and it was centered right there at the origin. And so now notice how this minus 2 shifted us to the right 2 units. When you're inside parentheses, you're going to find that horizontal transformations occur opposite of the way you would think. So this minus 2 actually is going to shift y equals x squared right 2 units. Because a minus you typically would think would go negative. When it's inside parentheses, it goes opposite of what you would think. So it would go right 2 units. And so our new points that we found here were 3, 1, 2, 0, and 1, 1. Okay, so noticing how similar then example 5 is, if I have x plus 2 in parentheses squared, then we should expect that this is going to shift our graph y equals x squared. Since it's plus 2, we should find that this shifts us left 2 units. Let's prove it to you. Okay, so I just chose a table here, chose some values. Let's plug these values in for x. Negative 3 plus 2, that's going to give me negative 1 squared, so that's positive 1. That's going to give me 0 squared. Negative 1 plus 2 will be positive 1 squared, that's 1. Now if we plot this, negative 3, 1, negative 2, 0, negative 1, 1. Here's our parabola. And sure enough, original vertex was here at 0, 0. Now I've been shifted 1, 2 units to the left. Okay? So write our points here, negative 3, 1, negative 2, 0, negative 1, 1. So again, just to summarize, what happens whenever you are inside parentheses, those are horizontal movements, meaning you're moving left and right. Horizontal movements are opposite of what you think, okay? So if it's minus, then you actually go right. If it's positive, you actually go left, all right? When you see a negative associated with your function, that's always in reference to a reflection. When the negative is on the outside, that's what you're seeing here. Let's see what kind of reflection that we get. So you'll notice here f of x equals negative x squared, and I went back to choosing negative 1, 0, and positive 1. My function is already has a negative here, so I have the negative that exists with the function, and then in place of x, I'm putting negative 1 squared. Okay. Function has a negative. In place of x, I'm putting 0 squared. Function has a negative. In place of x, I'm putting a positive 1 squared. So now with that first one, when you take a negative 1 and you square it, you get a positive 1, but then you have the negative sitting out front, so that's how I'm getting a negative 1. 0 squared is still 0. 0 is neither positive nor negative, so it's still 0. 1 squared is 1. Bring this negative down, so negative 1. So now if I plot these points, negative 1, 0, 0, 1, negative 1. So now if I graph these, you'll notice here, there is our new graph. This is the graph of y equals negative x squared. Let me just remind you of y equals x squared on the same graph. Y equals x squared was here and here. So look like that. It's not perfect, but you get the idea. Okay, there was your graph of y equals x squared. So as I mentioned, a negative is always associated with a reflection. You can either reflect over the x-axis or the y-axis, and so hopefully you would agree here that this graph has been reflected over the x-axis. They should be identical, so that if I were to fold it over the x-axis, the red curve would be on top of the blue curve, or vice versa, the blue would be on top of the red. So here, it was reflected over x-axis. Reflected over x-axis. And in general, when the negative is on the outside, you will be reflected over the x-axis. And we'll just write our 3 points here, negative 1, 0, 0, 1, negative 1. All right, we'll flip it on over. You'll notice here in example 7 and 8, we're looking at something different. We are looking at coefficients in front of our x squares. What do those coefficients do? So in example 7, we put a positive 2 in front of our x squared. So let's look at that. So I have 2 times, let's see, negative 1 in parentheses squared, 2 times 0 squared, 2 times positive 1 squared. You've got to do the order of operations, so think about it. You've got to square first and then multiply. So this would be 2 times negative 1 squared would be positive 1. And then 2 times 1, of course, is 2. Next one, 0 squared is 0, so 2 times 0 is 0. Next one, 1 squared is 1, so 2 times 1 is 2. Let's plot these points. Negative 1, positive 2, 0, 0, 1, 2. Okay, here's our new graph. And it might be helpful. Let me write that was the graph of y equals x squared. 2x squared, shoot. Sorry. Y equals 2x squared. That was y equals 2x squared. Y equals 2x squared. All right, let's do it in red here. Let's do our original parent function. It also had a 0, 0, but it was at 1, 1, like so. And then we also knew that it was at negative 2, 4, and at positive 2, 4. There was your original function. This is actually referred to as a vertical stretch, because you'll notice that your original function, your y value here was 1, but now since you multiplied it times 2, now your new y value is 2, so you're stretching it up. This is referred to as a vertical stretch by a factor of 2. It's just the number in front of the x squared, okay? So that's all that's happened there. You're affecting your y values. Like the x values have stayed the same, your y values have gotten larger, because before it was the 0.11, now it's the 0.12, for example. All right, so that's one of our points. Before it was the 0.00, it's still the same 0.00. Now this one was -1, +1. Now it's -1, +2. Okay, that's the difference. Okay, you have stretched it vertically. You've gone up with it. Okay, let's now explore, what does a 1/2, what does a fraction do in front of your function? Okay, so I just get a different color here. Y equals 1/2 -1 squared, 1/2 0 squared, 1/2 +1 squared. So again, order of operations, you got to square before you can multiply. So this is going to be 1/2. Negative squares is going to give me +1. Half times 1 is still half. 0 squared 0, so a half times 0 is still 0. 1 squared is 1, so a half times 1, still half. So now we plot -1, 1/2, 0, 0, 1, 1/2. So now here's our new graph. Kind of gotten a little wider here, right? This is our graph of y equals 1/2 x squared. Let me do the same thing I did for you before. Let's graph that y equals x squared on the same spot. So 0, 0 they share. This was 1, 1, -1, 1. So it kind of looked like this. So notice how your x values have still stayed the same, but notice how instead of your y value, originally you were at the point -1, 1, now you're at the point -1, 1/2. In this case, you are vertically shrinking your graph. So this is a vertical shrink by a factor of 1/2. So we had -1, 1/2, 0, 0 won't change on you, and then 1, 1/2. Because before we were, because this is, remember, this is the graph y equals x squared, so this is your parent function. Original y value was 1, 1. Now your y value is, your x value is still 1, but now your y value is 1/2. So you have vertically shrunk it. All right, so in general, when you have a number outside of the function, that's affecting you vertically. It affects you how you think it would, okay? That if it's a whole number, you're going to be stretching it, making it bigger. If it's a fraction, you're going to be shrinking it, making it smaller, okay? So again, vertical transformations always occur the way you think that they would. Horizontal ones are the ones that are opposite. So example 9 through the rest of this note, the rest of these notes actually are essentially a repeat of what we were doing, except for example 11. Okay, that'll be the only one that's different, but I do believe you'll be able to see that from the solution key as far as what happens. But anyway, this will give you, example 9 is a new parent function. F of x equals the square root of x, okay? And so now you want to explore, okay, now if I plug these values in for for x, what does the square root of x function look like? And then when you flip it over, what does the negative on the outside do? Remember, negatives are going to be a reflection. One of these is going to be over the x-axis, the other is going to be over the y-axis. I'm going to let you explore that. It has to do with whether it's inside or outside, okay? And then lastly, in number 12, you've got a number outside. We just got finished talking about that. When the number's outside, that's affecting you vertically. Think about whether it'll be a stretch or a shrink, okay? And again, this will really help you as we move into the transformation section for your Math 171 class. All right, let me know if you need anything. Thanks a lot. Bye. You can check yourself by the solution key.